Okay, this video is for the density handout that we're going to work on. It's one page front and back, so if you printed that first handout, it's a Word document. These look a little different. The density and geometric design were not part of the curriculum package that all the other ones are from, that familiar layout. This didn't have any for density or geometry means, so you get what I created from last year, which is just basic Word input. So the standards, we used to do it by standard, so the standard for this one is applied quantities of density based on area and volume and modeling situations. So density, we could just talk about density in terms of mass and volume. In this class you don't have to find the mass of anything, but for volume we've just been doing the volume unit, so you should be able to figure out the volume for lots of things. And if I give you the mass, you can do mass divided by volume and get the density. Okay, so you've seen it probably in your science classes as D equals m over v. Mass is typically in grams for our problems, and then the volume can be in cubic centimeters or any kind of cubic measurement. So remember, we just did volume with changing with similar solids, so anything raised to the third power is going to be a volume for us. And then population density is very similar to that. This is usually talking about an object, but population density is talking about people. So instead of the mass being a particular weight of an object, it's an amount of people. So the population density, so I'll just call it PD for population density, is the amount of people per area. And area, remember, is a square unit, so it's centimeters squared or feet squared or something like that. So those are the two formulas that we're going to use over and over. These are the two things that you had to calculate for this unit, so that's some of the things you're going to have to find in order to solve the problems for the density or the population density. So just 8 problems for density, so not a ton of problems on there, but they are all word problems and multiple steps typically, because you're finding the volume first, and then you're doing the mass they give you divided by the volume, or if they give you the density, you're working backwards to find one of these. Same thing with population density. We're going to be calculating the area like we've been doing, or like we did in the first couple topics of this unit, and then we're going to use the amount of people and work back, divide that by the area we get to find the population density, so how dense something is. So density, what it really means is like how heavy something is that may have take up the same amount of space. For instance, you might have a can of water, or a can of soda versus a can of sand. The sand is more dense, it's heavier. So they might be in the same container, but density talks about basically the weight of it. Which one will feel heavier with that same amount of volume. So if something is dense, it's a lot heavier for the same size as something else that may not be as dense. So for the examples for these, so that's really the notes part. The examples, if a certain block of lead has the dimensions of 5.2 inches by 4.5 inches by 6 inches, and it's a rectangular prism, and it weighs this much. So this weighs part, the grams, is our mass. Then determine the density of the block of lead. So we're going to be using this first one. They've given us the mass, and we need to determine the volume of a rectangular prism. So this is where this geometric design unit and the density kind of is a good, that's why I put it at the end, is because you had to really understand area and volume to do well on this part. But let's just say we have a rectangular prism, so we can just draw a rectangle and then an overlapping rectangle offset, and then we would just connect the top left corners, the bottom left, bottom right, and top right as best you can. So the dimensions are 5.2, doesn't matter which one is which, 4.5, and then 6. So we want to figure out what the volume of this prism would be. So remember, volume is taking a area, so we figure out the area of the base shape, which is a rectangle, which in this case is 5.2 times 4.5, and then we times that by filling it up, we times it by the height. So we have to have this layer 6 inches high, so we multiply all 3 of those numbers, so our volume is going to be 140.4 cubic inches. Okay, so that's the volume for this particular block of lead. So density is equal to mass over volume, and they've given us the mass as 1587 grams. And we just calculated the volume to be 140.4 inches cubed. And so density's measurement units is going to be grams per inches cubed. So basically, this is how many grams it can hold when we divide it for that amount of space, or that capacity. So when we just divide that out, our answer is going to be to the nearest, it doesn't state, so we'll just put 11.3 grams per inches cubed. Okay, that's how dense the lead is. So pretty packed in there, pretty heavy. Something that has, yeah. Okay, so looking at number 2, a rectangular block of materials on your dad's desk that acts as a paperweight. So there's something like a calculator holding papers down so they don't move, but it's not a calculator, it's a rectangular block. And the measurements are given here, and the mass is given. So we want to determine if the paperweight, what type of material it's made of. So this list gives us the density for each one. So what we want to do is figure out what the density of the paperweight is, so we can tell what kind of solid it is. So just looking at this list to kind of talk through what density is. So the weight per cubic centimeter is the biggest for platinum. So that's the most dense, it's the heaviest. Even like a coin size of platinum would be way heavier than like a coin size of marble, for instance. So the higher the number, the more dense. So what we want to do is figure out the density. So density is mass over volume. So we already have the mass. We need to calculate the volume. And we know volume for any rectangular prism is the area of the base. So for the 3 by 4 by 6, we can do 3 by 4 for the area of the base shape, which is just a rectangle, times it by 6. So 12 times 6 is 72. So this would be 72 cubic centimeters. Notice our units match up. So this was in grams, the mass was in grams, and the volume is in cubic centimeters, which is perfect. So we have density equals mass over volume, and our mass is 184.32, and our volume is 72. Okay, so when we divide that, that'll tell us our density, which is 2.56 grams per cubic centimeter. So the material on your dad's desk is marble. So the first 2 examples were of just regular density. The next 2 examples are population density, and then there's some things on the back for extra practice. So population density, and I'll just, so population density is, again, people per square, or per area, so it could be like square feet or square, in this case, kilometers. So Beijing has 20.7 million people in an area. So for Beijing, I'll do that one first. It's got 20.7 million people. Our abbreviation for people is PPL. And then area is 16,400 kilometers squared. And then Shanghai's so they want to know how many times as great is the population density of Shanghai as Beijing. So this should be more for the Shanghai one. So let's see, 20.7. You can just write it as 20.7 since these are both in mils. You don't have to write all the numbers behind that. And then divide that by I can just do 16.4 and just make all of these to the nearest thousand. So divide by 16.4. So we're talking about 1.26, and that's in million people per 1,000 kilometers, really, because we did remove the decimal spot a little bit. So I'm going to leave that number stored in my calculator, so I'm going to store it in spot 1 so it memorizes it. Then 23.7 divided by, I moved the decimal 3 times here, so I'm going to move it 3 times and do 6.3. So that one's 3.76. So if I do that, divided by, recall what was in spot 1, it's really close to 3 times. So how many times is great? If we divide, okay, so that's AD population density, it's just people divided by area. So on the next one, if they just give you the area and the population density, you have to work backwards to find the population. So population meaning people, and they gave you on this one, I'm just going to write the formula again. The population density. So they give you this side, and they give you the area, and you're looking for people. So to get people by itself, you would multiply both sides by area. So really you're going to be doing that people equals population density times the area. Okay, so we're working backwards. Basically, if this is divided, to get people by itself, you multiply both sides by area. Okay, but I'll let you do this and try it. Oops. Okay, for 5, it's a population density one again, and it's pretty straightforward, so I'll let you figure that one out. 6, I want to talk about water displacement. So if something is dropped into a glass of water, then the displaced water has the same volume as the object that was dropped into it. So again, the volume of the object equals the volume of the displaced water. So by displaced water, that just means like, I'll just try to see if I can do an example. The glass. So if I have a glass of water, and it's going to be difficult for you to see without me tipping the water on my papers, but it's at a certain height. So it happens to be right next to the word serve teams initially. If I were to take, well, I'm not going to use my watch. If I take this object and drop it in here, the water level will rise because the volume of this object is pushing the water level up. The volume the amount of space that this object takes up is now being, the water has that amount of volume of the water has been moved up. So if you can calculate the amount of water that was displaced based off of the rise of the water, then you can calculate the volume of the object. So it's telling you how much space the object is taking up. So a chunk of metal is dropped into a container of water, and the water rises 2 centimeters. So really what we care about is the 2 centimeters. So we don't know what initially the water was, but we know that the displaced water is 2 centimeters high. If the container was shaped like a cylinder, so I had already read that part, with a radius of 2, what is the density of the metal? So you're basically going to need to figure out the volume of a cylinder with a 2 centimeter height and a 4 centimeter radius. And then once you have that volume, you can do the density, mass over volume. Okay, so remember the volume of any object is the area of the base shape. So the volume of this would be capital BH, and the base shape is a circle, so we plug in the area of a circle formula, which is pi r squared. So pi r squared is the B, is the area of the base. capital B is different than lowercase b. And then you would plug in your radius of 4 and your height of 2 and get the volume. Then once you get the volume, you can plug it in with the mass and find your answer to the nearest tenth. Okay. So I'll go ahead and do this one all the way out. 4 squared and 2. So 16 times 2 is 32 times pi. Well, let me show you on here. 32 times pi is about, whoops, 100.5. This was in centimeters cubed. So I'm going to store that in spot 1. Okay. And then I do mass, so 60 divided by, recall what's in spot 1. And it's about 60, to the nearest tenth would be 0.6 grams per centimeters cubed. So again, displaced water, because volume is talking about how much space something's taking up. If there was an original water level and something was placed inside of it and completely enveloped with the water, then that amount of space that object takes up is how much the water has been displaced by. So we're just finding the volume of the displaced water, which gets us the volume of the object. Okay, so then density is given. And so this is very similar. You're still needing to use density's formula, but you're working backwards like you did on number 4. So I'll let you do that. And then another population density where you're having to find the area. So just to remind you, you can divide these shapes that, like for 5 and 8, up into different pieces so that, because we don't have an area for a shape like this, but we do have an area for this shape. And then we can find the area of these 2 shapes. Okay, so area of 1, 2, and 3. The other way to do that would be to find the area of the full rectangular piece as if this was included, and then just subtract out this rectangle. But you can either add area of 1, 2, and 3 to find the area, or you can subtract. But I'll let you do the rest of that. Well, actually, I'll do this one. Okay, so the area of the shape, area of the first, area of the second, and then area of the third. So we have 3 different areas. So the area of the first shape, we have a 5 by, okay, so the 10 here is talking about this length. This whole thing is 20, so that means this part of it up to here is 10. And this is given us as 5 here, so there's 10 and 5 is 15 on this part, so there's 5 left hanging off over here. So this is a 5 by 5. So the area for this square on the left is 5 by 5. This rectangular piece, the whole thing was 18, but we took out 5 units. So we're left with 13 here. So that's a 13 by 20. And then object 3 is also a 5 by 5. So the area of the whole shape would be 25, 25, so 50 plus 13 times 2 is 26, so 260 plus 50. So 260 plus 50 is 310. It's area, so it's meters squared because we times meters by meters, and then we added it to another meters by meters. But when you're adding meters squared, you still just get meters squared, so it's like same unit, so we're good. So we did 25 plus 260 plus 25. Just wanted to double check my mental math. Okay. If the population density, so they're giving us the population density. So normally it's PD, population density equals people over area. And they're giving us the population density. So we have that number. What is the maximum capacity? So that's how many people can fit in the room. So that's X. And the area was 310. Multiplying both sides by 310 gives us that a maximum of 7,750 people can fit. Okay, if you have any more than that, then you're going to be a little over the capacity density requirements.